Good morning, students. Good to see everybody online again today. I just wanted to cover one quick thing that I didn't get to last time I made a video, and that is this thing called atmospheric pressure. I think the last thing I said on the last video might have been that people say when you live at higher elevations that, when you go mountain climbing or skiing, things like that up in the mountains, that you can't breathe as well because the air is thinner or there's not as much oxygen available. Well, that's actually not completely true. When we talk about the differences between pressure and volume in respiration, I mentioned last time that I made a video that when this thoracic cavity space, the volume is made larger, the pressure decreases, and that causes a natural inflow of air. But what causes the inflow of air is this thing called atmospheric pressure. So, where you live on the planet depends on or determines the atmospheric pressure there. And so, if you live high on a mountain, the atmospheric pressure there tends to be lower, which means that air is not going to be forced into your lungs as efficiently or as intensely as it would be at places of lower elevation where the atmospheric pressure is quite higher. And so when they say that we're having trouble breathing at these elevations, that's why the air is not being forced into the lungs by this atmospheric pressure, because atmospheric pressure at higher elevations is not as large or intense. I don't know quite the right word for it, but anyway, email me if you have any questions about that. Okay, so let's jump into the third set of Cornell notes. The first question is pretty straightforward. These are things that aren't respirations, but they are movements of air called non-respiratory movement of air. I think that makes sense. I'm not going to spend a lot of time with the respiratory volumes and capacities. Later on, you'll study that more intensely, especially if you're going to go into any kind of respiratory therapy or, those different fields of medical study. They do have diagnostic values in terms of understanding how much air people are taking in, how much they can utilize in terms of gas exchange, but we don't have time right now to talk about all of that. So, question two goes into talking about respiratory sounds. So, when you have a patient come in, you're going to be listening with your stethoscope to their lungs, like you've probably had done to you. You're listening for bronchial sounds and vesicular breathing sounds. And so, basically, to make a long story short, what you're listening for here is the movement of air into these respiratory passageways or down into the alveoli. Because if your patients can't breathe well, if they can't exchange gas as well, you've got to figure out why. And so, one of the diagnostic tools we use is a stethoscope to find out what's going on and where is the problem. This is something we don't have time to go into. Let me go back here just for a second. Your book here talks about listening for different sounds that you would hear during an exam. And when they talk about crackling, wheezing, and rails, those kinds of things, you should have included that on your Cornell notes. Okay, so go back and look for those in the chapter if you haven't read those yet. So when we talk about transport of oxygen through the blood, we've talked before about this molecule called hemoglobin. And you see here that basically what oxygen does is it hitches a ride, like as in a pickup truck, on the molecule hemoglobin. What's needed for that is this molecular structure of these different parts of hemoglobin in addition to iron. And so let's talk a little bit more about this transport of oxygen. So it happens on the molecule hemoglobin. So when we see these red blood cells here in the body running through these capillaries at this respiratory zone, here on the red blood cell is where hemoglobin is found, and it's carrying oxygen. Okay. And so when this oxygen is transported to this respiratory zone, remember that where there's a high concentration of oxygen, oxygen is naturally going to diffuse into this area where there is a low oxygen concentration. Vice versa, where there's a high CO2 concentration, it's going to naturally diffuse out to where there is a low CO2